Our last lesson was about sums and differences of functions. Today we move on, of course, logically to products and quotients of functions. So here is f times g at x. That's the same as writing f at x times g at x. So sometimes we're more comfortable writing functions like this. Division is the same. You can break them apart, but just remember that our g at x function won't be able to be, it won't equal 0, can't equal 0. We have this symbol for the intersection of two sets. It's like an upside down U, and it means intersect. When combining functions, the new domain is the set that contains the x elements, the values that are common to both sets. This is the symbol for intersection. Denominators can't equal 0, so we would exclude those. That's this one down here. If we have one domain that has the numbers 1, 2, and 3, and 4 in it, then this other domain B has 3, 4, 5, and 6 in it. Well, the intersection of those is just 3 and 4. Those, you probably can't read them, but those little numbers in the middle of the blue part. The intersection is just the parts that overlap. The U symbol, we've used that a lot already, and it represents the union of two sets. So we're not really talking about that for the domain here. We do use this to say when we have two completely different domains, sometimes if we have to put them together, to represent the domain. But for now, we only want the parts of the two domains that overlap or intersect. So this we use more often when we would say a function is increasing when x is from negative infinity to 3, and then again from 4 to infinity. We would use the union symbol to show that we're putting them together. Example 1, we have f at x and we have g at x. F at x is a radical and g at x is an exponential. We have to find the domain of f plus g, state the domain of f times g, and state the domain of f divided by g. So this one's kind of review, so we'll start with that one first. The domain of f plus g. So let's first list what the domain of f is and the domain of g. I'll do f at x in red here. So the domain of f at x. What is the domain of f at x? That's a radical. So remember, we can't have a negative under the radical sign. So we look for what would make underneath the radical sign equal to 0. And that would be when x is negative 4. So it's going to be something about negative 4. So is it when x is less than negative 4 or when x is greater than negative 4? So if you can't remember how to tell, just sub one of the numbers in. Sub in a number less than negative 4, like negative 5. What would happen if you subbed a negative 5 in here? Well, then we'd get a negative. So we know that we're looking for that our domain has got to be x is greater than or equal to negative 4. That would be our domain for f at x. Now what about the domain of g at x? That is a exponential. So the domain of g at x, that one is a little more straightforward. It's just x is an element of real numbers. No restrictions on our x values there. So now let's go down to part A, which says find the domain of f plus g. So the domain of f plus g is the intersection of these two. It's the intersection or the overlap. So the intersection, where do they intersect? And usually if you have one like this, x is an element of real numbers, that's everything. So you really end up just using the domain of the one that has the restrictions, because that will be the one that has the intersection. So the domain of f plus g is, the domain is equal to, so using our full set notation here, x is an element of real numbers such that x is greater than or equal to negative 4, because that part of the domain exists in both functions. That part of the domain exists here and it exists here, and we can only take the intersection of those. So that's f plus g. Now what about f times g? So the domain of f times g, if we f times g is the same as writing them out separately, f at x times g at x. So it's the same thing. We're looking for the domain of f at x And we're looking for the intersection of that with the domain of g at x. So that is the exact same that we just had for the previous question. The domain of f times g is x is an element of real numbers such that x is greater than or equal to -4. Okay, it's the same. What about the domain of f divided by g? So this one's a little bit different. The domain of, oh, look up here at our original, our second bullet. G at x cannot equal 0. So our denominator cannot equal 0. And our denominator in this case is g. So g is 2 to the power of x minus 3. That cannot equal 0. And I bring the 3 over. 2 to the power of x cannot equal 3. So here you need to get out your calculator and maybe do your change of base formula for logs. That is, remember, log. So this is a great review for your final exam. Log of 3 over log of 2 is going to be x. So we get approximately 1.6. So now to write out the domain, I'll just put it over here. This is approximately 1.6. So the domain of f divided by g, domain of f divided by g is x is an element of real numbers such that, now don't forget, we're not just going to jump right to saying x cannot equal 1.6 because we have this other restriction here too, right? X has to be greater than or equal to -4. So we have to include both of those. X has got to be greater than or equal to -4. That's part of it. And also the restriction of x cannot equal 1.6. Just barely fit that in there. So the domain of f divided by g is a little trickier than the other two. Example 2. F at x is a cubic. G at x is, well, it's a radical with a negative exponent. That's new. Determine the equation of the function f times g at x. Remember, we can write it instead as y equals f at x times g at x. So let's just substitute in with our equations. F at x is 5x cubed, and g at x is square root of x to the power of -5. So our last lesson, I told you if your functions aren't the same type, you often can't go any further. We can go further though with this one because I'm going to get rid of radical form. We either want radical form or exponential form. It's usually easier to go with exponential form. So instead of the square root of x, square root of x is the same as x to the power of 1/2 to the power of -5. So that's 5x cubed times x to the power of, we multiply these two, that's a power of a power, -5/2. So since our bases match here, we can add the exponents. Our 5 is the coefficient, and now the base of x, I'm just going to write that once. I have an exponent of 3, and I have to add on to it my -5/2. So really I'm subtracting 5/2. So 3 is the same, so I'm doing 3 minus 5/2. That's the same as 6/2 minus 5/2. So that's 5x to the power of 1/2, or you could write 5 root x. So that is our new function of the product of the two functions. Now we need to find the domain, and we're going to draw it on a number line. So let's go back again to our original question here. The domain, let's start with the domain of f at x first. What's the domain of f at x? So domain of f at x is, that's a polynomial function. So those are great. That's just x is an element of real numbers. How about the g at x? The domain of g at x? Domain of g at x, what's that going to be? Is there anything that x cannot be, well, sure, we've got a square root there, a radical. It can't be negative. And that just leaves us with x is an element of real numbers such that all the x's we can use must be, okay, greater than or equal to 0. What do you think? What do you think about greater than or equal to 0? Well, there's a problem with that. Do you know what it is? The problem is this is a negative exponent here. So really, this is the same as saying 1 over the square root of x to the power of 5. That's g at x. So denominator can't be 0, so we actually can't have a 0 for x. I'm going to have to erase that greater than or equal to. It can just be greater than 0. I can't have 0 in the denominator there. The domain of our new function, domain of f times g at x is, remember, it's the intersection of these two right here. It's the intersection of these two. So the intersection of these two, it's always easy when one of them is x is an element of real numbers, because that one you don't even have to think about it. You really are just going to go with your one that has the restrictions. So it's nice when one of them has no restrictions and one of them does, because you don't really have to put the two of them together. So the way I draw this on a number line is I get a ruler and I'm going to draw a horizontal line, and a number line looks like this. We put the number of importance in the center, and our number of importance here is 0. So I'm going to put that in the center, and just a few numbers, up 2, 4. I could have counted by ones, it doesn't matter. -2, -4. My domain of f times g is the intersection of those two, so it's going to be an open circle on 0, not closed, because we're not allowed to include 0 because of that denominator problem, and then everything off to the right like this. Okay? So that is our number line domain for f times g. And we're never done with rates of change, so we're going to find the rate of change for our answer for A. That's one of these two here. We want to find the rate of change when x equals 4. We want to find the instantaneous rate of change. So we're first going to start by calling it an average rate of change, because until h is equal to 0, it's an average rate of change. So we're looking for the average rate of change, and the formula is f at a plus h, or you could say x plus h. Actually, let me put an x there. It makes a little more sense for this one for it to be an x than an h. F at x plus h minus f at x over h. So what is x and what is h? Well, x is 4, h stays h, because we are algebraically manipulating. We are not subbing in h equals 0.01. That's just the difference quotient, but we're algebraically manipulating. So I'm going to leave it alone. F at x plus h, so that's f at 4 plus h minus f at 4, all over h. So up to our function here, it doesn't really matter which one you sub into. You can use the exponent or the radical. Let's use a radical because I want to do some rationalizing. So I'm going to sub into this one here, subbing a 5 plus h in first. I get 5. And then under the radical, instead of x, we put a 4 plus h. 4 plus h, and then f at 4 is 5 times the square root of 4, and that all goes over h. So we can simplify a little bit. Square root of 4, I'm looking at this one right here, that's going to be 5 times 2, right? So 5 times root 4 plus h minus 5 times 2 is 10 over h. I'm going to have to move up here because I don't have enough room. Up here. So we're still on the average rate of change. average rate of change, and we're trying to simplify. Remember, the whole goal is to get rid of that denominator of h. This one's a little harder. There's, I'm going to factor out the 5, the coefficient of a 5 here. See if that makes it look a little bit better. So factor out a 5, I get 4 plus h minus 2 over h. Well, it would have been better if I could have factored out an h, because then I could at least cancel out the h's right now, but I'm not at that stage where I can cancel out the h's, so factoring the 5 didn't help too much. I could have left it alone. So what I'm going to do here, and I could have done it on the previous step, but I'll start it here. I'm going to multiply by 1. So this, what I'm going to do here is not necessarily stuff you would have thought of to do on your own, but I'm going to multiply by the square root of 4 plus h plus 2, square root of 4 plus h plus 2. So let's see where that gets us here. So we have a 5. Let's just leave that 5 out for now and not worry about that. I'm going to get a square bracket because I'm going to distribute all this numerator stuff here. Okay. So let me just put a bracket here just to show you. This is a binomial, and this is a binomial. So what I'm doing here is binomial expansion. First thing I have to do is root 4 plus h times root 4 plus h. What is root 4 plus h times root 4 plus h? Well, there are 2 of them, right? So it's root 4 plus h squared. And really, that means I can get rid of the power of 2 and the radical. So I'm going to do that right now. So I really just have 4 plus h. That's the first step. Let me tidy that up. Now I'm going to multiply this first term by the last term. And that's a 2 is an integer, so I can't multiply it into the radical. Those don't go together. So I'm just going to have to write it as 2 root 4 plus h. And now I'm going to multiply these 2 together. That's minus 2 times root 4 plus h. And then we go to our last ones. I'll use orange for that. The last ones are negative 2, whoops, I overshot there. Negative 2 times positive 2. That's going to be a negative 4. So there's our numerator. And the denominator. I'm going to just kind of squeeze the denominator together. I'm not going to actually multiply because remember, I want to cancel out h's later, so I don't want to distribute it all in with everything. 4 plus h minus 2. I'm going to leave it like that. Okay, looking at my numerator, what can I do here? Well, these 2 are going to cancel. And we knew something was going to cancel when we did this because we multiplied by the conjugate. So this one was what my radical minus 2, so this one was my radical plus 2. By multiplying by the conjugate, I have one positive of that multiplication piece, and then I have one negative or one subtraction. So these are going to be gone. These red ones are going to be gone. And I'm going to be left with 4 plus h minus 4. So let me just cancel some of this stuff out here. So these 2 are gone. So I have 4 plus h minus 4. Well, the 4's are gone. 4 minus 4. All I've got left now is 5 and an h. So I can just multiply those 2 together because that's all that's left in there. All that's left in that whole bracket is an h. So 5 and then an h. So we'll just put that together and we get 5h, and we're going to be able to cancel over h times 4 plus h minus 2. Okay, here we go. Now we can cancel our h's. And now we can state that we're at that great step that we get to. Once we cancel our h's, we can now let h equals 0. We're looking for where h approaches, as h approaches is 0. That's what we're trying to find for our instantaneous rate of change. As soon as we do this, we can now write instantaneous rate of change instead of average. Instantaneous rate of change. is equal to 5 over, so we're letting it approach 0, remember, so we're putting a 0 in here. Root 4 plus 2, sorry, there's a plus 2 there, sorry. Plus 2, root 4 plus 2. And I knew that as soon as I started writing this, I thought, what are we getting 0 for? We shouldn't be. So that's 5 over 2 plus 2, 4. There is our rate of change when x equals 4. There's our final answer right here, 5/4. All right, we got a nice clear answer from algebraic manipulation, although it was hard, especially with this new radical step here that we multiplied by the conjugate in order to reorganize our numerator a little bit. Our last example is a big one. We need lots of writing room here. You may run out of space if you're using the handout. Recall from chapter 5 that rational functions are quotients of polynomial functions. So that's what rational functions are, right? They're quotients of polynomial functions where f at x equals p at x over q at x. That's what a rational function is. And of course, q at x cannot equal 0. So here's our p at x, here's our numerator, here's our q at x, that's our denominator. First, we're going to factor p at x and we're going to factor q at x. Great review here. Factor p at x and factor q at x. So let's look at p at x first. Well, there is an x in every term, a common factor of x. Let's factor that out. It's not even just an x that we can factor out. I can factor out an x cubed here. I get x squared plus 8x plus 16. Now, what about this bracket? Can I factor that further? It's a nice trinomial, is sum and product or crisscross, whatever your method is there. Yes, we can factor that further. It's going to be x plus 4 times x plus 4 or x plus 4 squared. So there's p at x factored. How about q at x? Let's change colors for q at x. Q at x. Q at x. Common factor there? No. There's a lot of terms for q at x, so I'm going to have to try out the factored theorem here. So we're looking for factors of 9. We're trying a plus 1, a minus 1. We're trying a plus 2 and a minus 2 and a plus 3 and a minus, oh sorry, no 2, plus 3, minus 3, and then 9. So which ones work? I will get you started here. The first one, q at 1 is going to equal 0. So you should have got that one pretty quickly. Q at 1 is equal to 0. That means we have a factor of x minus 1. It's a factor. Okay. X minus 1 is a factor. What do we do with that? Okay, let's say we're going to do synthetic division here. We put a 1, draw our little operation or symbol here, and our coefficients go in the front. That's a 1, a 4, a negative 2, negative 12, and a 9. So I want you to press pause and do your own review here of synthetic division. When you come back, this will be done. So of course we have a remainder of 0 because we already knew that was a factor. We already knew we would get a remainder of 0 here. These terms leave us with the coefficients of another polynomial. So what we have here for q at x so far, we've got q at x equals, and we got our x minus 1. And then we have x to the power of 3 plus 5x squared minus 3x minus 9. That's our constant at the end. So we have to do this all over again. So with our new, let me erase this line here, with our new cubic, our new polynomial, we're going to have to find another factor. And again, our constant is a 9. So Try +1, try -1, try +3, try -3, try +9, try -9, and you'll come across one really quickly. Again, it's 1. So we're just talking about this section here now. So just looking at this piece, I know that x minus 1 is a factor of it. So I can either do long division or do my synthetic division all over again with a 1 and with my new coefficients 1, 5, -3, -9. So you're going to do that, and then when you're done here, what you get is a quadratic that will factor again. So I want you to press pause now, and when you come back, I want it to be completely factored. And that is what you should have for Q at x. So I'm going to erase all of this here, and I'm going to put just my factored form in there because I need more room. So if you haven't written that down yet, do it now because I'm about to erase it, and I'm just going to write Q at x in factored form. Oh, there we go. Now part B says write the equation of y equals p divided by Q at x in factored form. P divided by Q at x. Let's write it like this: P divided by Q at x in factored form. That's our y. That's equal to, so P at x was my numerator. That's x cubed. You're really supposed to write x's like this, right? But it's hard with the stylus that I have. They go crazy a lot. So I write my x's like multiplication symbols, and that's a big no-no. X plus 4 squared over Q at x is x minus 1 squared times x plus 3 squared. That's part B. So here comes part C. This is the big part here. We're going to graph P divided by Q at x, and we have two methods here. So let me just go over both of them slowly. So patience, please. First method is to graph P at x, right? You know how to graph that. Then graph Q at x. You know how to graph that. Just graph them individually. Then use these graphs to find new coordinates by dividing each y coordinate of P by the corresponding y coordinate of G. So you're just dividing. That's what we're doing. Try to find two coordinates this way. So we're not going to graph it. We're not going to do this. We're not going to graph this in red and graph this in light blue and then divide them all. So we're just going to come up with some coordinates. So first of all, P at x, P at 4. Now, sometimes it's easier to sub into the original without all the factored parts. So you can sub your 4 in right here if you want to, or you can sub it in here, whatever you like. What is P at 4? It's a big number. It's 4,096. Oops. I'm trying to fit it in there, and I'm trying to write small. 4,096. Now what's P at -4? Well, that's an easier one. That's 0. Okay, now let's go over to Q. Q at 4. Q at 4, sub in your 4, and you get 441. Q at -4 is 25. So what is P at x divided by Q at x? So the 4, we're not dividing the x values, we're dividing the y values. So we're taking 4,096 and dividing it by 441. We're not changing the x value, just the y value. So that's about 9.3. What about the P at -4? So remember, we have to have our domains are overlapping. So we're using the x value of -4 and we're dividing the y values. 0 divided by 25? 0. All powerful 0 there. So that's one way that you could, that's method 1. Method 1 means you would graph both, or you would get a whole bunch of coordinates on both, and then you would just divide them all. But we're going to do number 2. We're going to just graph this function right here because we know how. We've been graphing this and it's a great review for us. We're going to use the methods from chapter 5. Remember those zeros, asymptotes, end behavior, all that sort of thing. So we're going to, this step now, we're going to just jump right into graphing this piece right here. That's the method we're going to use. So let's start with the zeros. The zeros come from the numerator. The zeros, or the x-intercepts. Zeros come from the numerator. So x cubed gives me a 0. So I'm going to have a 0 at x equals 0. Is that a bounce? 0, that x cubed, is that going to give me a bounce? No, it's going to give me a bend, actually. I'm going to have a bend or a saddle right there, because the degree of that factor is cubed. I also have another 0 at x equals -4. That one's got a power of 2. The order of that factor is 2. So this one's going to be a bounce. So I'm just going to put the dots on for now. So I've got a bend here. Now the bend, again, I don't know yet if my bend is going up this way or if it's coming this way. I'm not sure yet. So we're going to get some more information. But I know I definitely got 0, 0 as a coordinate. And I've got -4, 0 as an intercept. Okay. What else have we got? Okay, we got the zeros. Zeros can be spelled with an OS or an OES. Asymptotes. Okay, let's look at the denominators. Asymptotes. Asymptotes. P-T-O-T-E-S. Vertical asymptotes. Vertical asymptotes. We have, look at the denominator. We have a vertical asymptote at x equals 1. And we have a vertical asymptote at x equals -3. But look at the order of those exponents in our denominator. They're both a power of 2. Power of 2 there, power of 2 there. It doesn't mean our asymptote bounces. Like this is a 0 that's going to bounce. Do you remember what that means? If you have a power of 2, if your order is 2 on your denominator factor, it means that you're going to have the same end behavior on your asymptote. So if I draw an asymptote here at x equals 1, either both sides are going up of my graph on their side of the asymptote, or they're both pointing down, or they're both coming from below. So that's what this means here. So this means they're going to have, they have the same same behavior, I guess is one way to say it, same end behavior. Okay, we talked about the vertical asymptotes. Do we have a horizontal asymptote? Now we're going to look at the degrees. The degree of the numerator, that's p at x. The degree of the numerator is 5. Put that up here. The degree of the numerator is 5. The degree of the denominator is 4. Since the degree of the numerator is greater than the degree of the denominator by exactly 1, do you remember what that means? It means we're going to have an oblique asymptote. So there's no horizontal asymptote, we're going to have an oblique asymptote. So our oblique asymptote, we're going to have to find out where that is. And how do we find the oblique asymptote? Well, we have to divide. And we're going to have to take our denominator and our numerator and divide them. So I'm going to set up long division here, but it's going to be long and messy. The part that goes to the left, the part that I'm dividing in, is q at x. This is x to the power of 4 plus 4x cubed minus 2x squared minus 12x plus 9. And that's going into x to the power of 5 plus 8x to the power of 4 plus 16x cubed. And oh, I don't have any more, so I'm going to have to put 0 placeholders in because I need 1 for every degree. 0x squared, 0x, and a 0 constant. Now we divide. Now the number, everything looks huge here, right? The dividend, everything looks huge. But that means it's going to be quick to divide, actually. So the first thing we do, remember, is we take x to the power 4, we divide it into x to the power 5. That is just x. Then we multiply this x back down into every single one of these pieces here. Whoops, I just deleted the x by mistake. That should be an x, sorry. So I multiply it back down, and I have x to the power 5 plus 4x to the power of 4 minus 2x cubed. Is that oh, that's a minus there. I could barely read my own writing. That is a minus 12x squared. Wrong red. 12x squared and plus 9x. So we subtract all of this stuff here. The first two, of course, are gone. We have 4x to the power of 4 plus 18x cubed plus 12x squared minus 9x. And I'm going to bring down this 0. Next, I take again the first term. That's the x to the power of 4. I divide it into my first term here. That gives me a plus 4. And that's going to be it. We'll go ahead and multiply it all through, although it doesn't really matter. Let me go ahead and do that. So we have our quotient here. We are going to have some remainder, but the remainder won't matter. It's not going to affect our oblique asymptote line. This is the equation of our oblique asymptote, y equals x plus 4. That's the equation of my oblique asymptote. So let's put that on there. Oblique asymptote x plus 4. So normally we graph lines. Well, we can do it a couple of ways. We've got a y-intercept of 4. So that's kind of a hard one to put on there, actually, because I have a 2.5 scale here. A y-intercept of 4 is about there. And then my slope is 1. I can rise 1 and run 1. I could also use the intercepts of the line itself. If I sub in y equals 0 here, y equals 0, I'm going to get x plus 4, bring the 4 over, I get x equals negative 4, so I get my asymptote is going to go right through the spot, which is a 0. I already put a dot there. I have an intercept there. The oblique asymptote is like a horizontal asymptote where it can be crossed, and it often is kind of in the center or the meat of the function, but it's to help us define end behavior. So it's okay if it gets crossed, and this clearly will because our asymptote is passing right through one of our zeros. So let's get our rulers and draw a line through our line of our oblique asymptote. Next, I'm going to put in my vertical asymptote, so I'm going to have to erase all this long division that I wrote in red, and so I have room to get on the graph. Okay, so we've done a great job here with our asymptotes and our zeros, and so now we're just kind of filling it in. We can get a few test points if we want to here, but we are going to definitely have a bend. Remember that bend 0 we had at x equals 0? So we're going to have a bend there. Again, I don't know if it's which way it's bending, but I can get I could get a test point. I could sub in, so let's say I could try maybe when x equals negative 1, just to get another point to see which way it goes. And I know that's going to tell me that it's coming increasing. So the section in the middle here, this section right in here, is going to be basically a cubic on its own. It's going to cross that oblique asymptote and it's going to bend at 0, and you can do a few test points to double check that. And if we want to do a really thorough review of asymptotes, what we would do is we would sub in numbers really, really close to this side of the asymptote, like 0.99999. I would sub it in, and I would find out I would have a really large positive number here, and I could sub in a number really close to this asymptote of negative 3. like negative 2.999, and I would find it I'm way down here. So we're going to draw something like this, whoops, like that there. Now remember when we talked about our vertical asymptotes, we saw they have the same end behavior. That means on the left side here, I know this one's coming, this side's got to be coming down, and on the right side of my asymptote at 1, it's got to be going up because of the exponents that were on those factors on the denominator. So that's helpful. I also know that right here we have a bounce, and so we're going to bounce around that 4, and then we're going to kind of run along. So let me connect my dots here. I'm going to start at this asymptote. Whoops, I shouldn't be kind of weaving around like that. I'm going to bounce here, and then I'm going to come along, kind of come along the asymptote like that. So that's a weird one. And these are a lot of these things I wouldn't expect you to know. I'm doing a really complicated one right here. There's so many things going on, but the reason I made it so complicated is it's good for you for review. I tried to get every type of thing in here. So the last piece of my graph I have, and you could sub in a value here like x equals 4 to get an idea of what's going on with your graph here. This one, 4 is going to give you, actually we did 4 right here, sorry. We already found that, 4, 9.3. So 4, 9.3 is right about there, and actually negative 4 is 0, we already graphed that one. So 4, 9.3, so that tells me that this is just kind of going along like that. That's what's happening there. So there is a very complicated and strange looking graph, but it has all kinds of features of it that each individual feature it's just that we don't usually put them all together like that. I have to erase some of this stuff down here because you have we have one more part of the question to do. Let's see if that's enough there. Yep. State the domain of P divided by Q in both set notation and interval notation. Domain. So domain and set notation. Set notation is the curly brackets. X is, of course, an element of real numbers, such that, for sure, such that. What are the restrictions on X? Well, those are our vertical asymptotes. X cannot equal, in order, negative 3 or 1. In interval notation, we write it like this. We're talking again about X's, and X is an element of or belongs to. So our x's are, so we think of this, remember, as a coordinate. The left-hand coordinate is negative infinity, and then that goes all the way up to negative 3. So square bracket or round bracket here? What do you think? Well, it's got to be round because we can't include negative 3. It's an asymptote. Now here comes my union symbol because I want to include this entire next set, which is on the other side of negative 3 all the way up to 1. Again, a round bracket because it's an asymptote. And so it's not an intersection of these things, it's all of these pieces. And a union with 1, and that last piece here. So here's my x value of 1. I'm putting it on the grid. Here's my x value of 1. So my graph exists all the way to infinity there. 1 to infinity. There's the interval notation for the domain. Lots of stuff in there, lots of review in that question to help you get ready for your final evaluation, which is coming up.